So hello everyone and welcome back to Neetopedia, that is Neetka Encyclopedia, and we are back with our chemistry audiobooks on inorganic chemistry. And the chapter is periodic table, but sarcastically we have finished hydrogen, S block, P block, D block, F block. That is the main chapters of inorganic chemistry, but we left out the main backbone of our inorganic chemistry, that is the periodicity and properties of elements. But let's undo our mistakes and learn from it and start with periodicity and properties. You can check all our chemistry audiobooks in our channel playlist. If not, just click on that I button of the video and you'll get the link to it. So without wasting our time, let's begin with Unit 3, Classification of Elements and Periodicity and Properties. The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students. It suggests some new avenues of research to professionals, and it provides a succinct organization of the whole chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities, but instead display trends and lie together in families. Awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of the chemistry, the chemical elements, said by Glenn T. Seaborg. In this unit, we'll study the historical development of the periodic table as it stands today as the modern periodic law. We'll also learn how the modern periodic classification follows a logical sequence of the electronic configuration of atoms. Finally, we shall examine some periodic trends in the physical and chemical properties of the elements. 3.1 Why do we need to classify elements? We know by now that the elements are the basic units of all types of matter. In 1800, only 31 elements were known. By 1865, number of identified elements had more than doubled to 63. At present, 114 elements are known. Of them, the recently discovered elements are man-made. Efforts to synthesize new elements are continuing. With the large such numbers of elements, it is difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists search for a systematic way to organize their knowledge by classifying the elements. Not only it would rationalize known chemical facts about the elements, but even predict new ones for undertaking further study. 3.2 Genesis of periodic classification. Classification of elements into groups and development of periodic law and periodic table are consequences of systemizing the knowledge gained by a number of scientists through their observations and experiments. The German chemist John Dobereiner in early 1800s was forced to consider the idea of trends among properties of elements. By 1829, he noted a similarity among the physical and chemical properties of several groups of three elements called triads. In each case, he noticed that the middle element of each of the triad had an atomic number of the other two. Also, the properties of the middle element were in between those of the other two members. Since Dobereiner's relationship was referred to as law of triads seemed to work only for few elements, it was dismissed as coincidence. The next reported attempt to classify elements was made by a French zoologist A.E.B.D. Chancortus in 1862. He arranged the then known elements in order of increasing atomic weight and made a cylindrical table of elements to display the periodic recurrence of properties. This also did not attract much attention. The English chemist John Alexander Newland in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weight and noticed that every eighth element had properties similar to the first element. The relationship was just like every eighth note that resembles the first in octaves of music. Newland's law of octave seemed to be true only for elements up to calcium. Although this idea was not widely accepted at that time, he for his work was later awarded Davy Medal in 1887 by the Royal Society of London. The periodic law as we know today owes its development to the Russian chemist Dmitry Mendeleev and the German chemist Lothar Meyer. Working independently, both the chemists in 1869 proposed that on arranging the elements in increasing order of their atomic weight, similarities appear in physical and chemical properties at regular intervals. Lothar Meyer plotted the physical properties such as atomic volume, melting point and boiling point against atomic weight and obtained a periodically repeated pattern. Unlike Newland, Lothamer observed a change in the length of that repeating pattern. By 1868, Lothamer had developed a table of the elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev, the scientist who is generally credited with the development of the modern periodic table. While Dobereiner initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. It states as follows: the periodic properties of the elements are a periodic function of their atomic weights. Mendeleev arranged elements in horizontal rows and multiple columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical column or group. Mendeleev's system of classifying elements was more elaborate than that of Lothamer. He fully recognized the significance of periodicity and used broader range of classification of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and the properties of the compound formed by the elements. He realized that some of the elements did not fit in the scheme of classification. In order of atomic weight was strictly followed. He ignored the order of atomic weight, thinking that atomic measurements might be incorrect, and placed these elements with similar properties together. For example, iodine with lower atomic weight than that of tellurium was placed in group 7 along with fluorine, chlorine and bromine because of similar properties. At the same time, keeping his primary aim of arranging the elements of similar properties in the same group, he proposed that some of the elements were still undiscovered and therefore left several gaps in the table. For example, both gallium and germanium were unknown at that time. Mendeleev published his periodic table. He left a gap under aluminium and a gap under silicon and called these elements as eka-aluminium and eka-silicon. Mendeleev predicted not only the existence of gallium and germanium but also described some of the general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for these elements and those found experimentally are listed in Table 3.3. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table famous. Mendeleev's periodic table, published in 1905, is shown in Figure 3.1. 3.3 Modern periodic law and the present form of periodic table. We must bear in mind that Mendeleev developed his periodic table. Chemists knew nothing about the internal structure of atom. However, the beginning of 20th century witnessed profound developments in theories about subatomic particles. In 1913, the English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the element. A plot of √nu, where nu is the frequency of X-rays emitted against the atomic number Z, gave a straight line and not the plot of √nu versus atomic mass. He thereby showed that atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was therefore accordingly modified. This is known as the modern periodic law and can be stated as the physical and chemical properties of the elements are periodic functions of their atomic numbers. The periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium, like actinium and proactinium, were also found in pitchblende, that is an ore of uranium. It stimulated renewed interest in inorganic chemistry and has carried into the present with creation of artificially short-lived elements. You may recall that atomic number is equal to nuclear charge, that is, number of protons, or the number of electrons in a neutral atom. It is then easy to visualize the significance of quantum numbers and electronic configurations in periodicity of elements. In fact, it is now recognized as the periodic law is essentially the consequence of periodic variations in electronic configurations, which indeed determine the physical and chemical properties of elements and their compounds. Numerous forms of periodic table have been devised from time to time. Some forms emphasize chemical reactions and valence, whereas others stress the electronic configuration of element. A modern version of the so-called long form of the periodic table of the elements is the most convenient and widely used. The horizontal rows, which Mendeleev called series, are called period, and the vertical columns groups. Elements having similar outer electronic configuration in the atoms are arranged in vertical columns referred to as groups or families. According to the recommendation of International Union of Pure and Applied Chemistry, that is IUPAC, the groups are numbered from 1 to 18, replacing the older notation of groups 1A, 7A, 8, 1B, 7B, and 0. These are altogether 7 periods. The period number corresponds to the highest principal quantum number of the element in the period. The first period contains 2 elements. Subsequent periods consist of 8, 8, 18, 18, and 32 elements respectively. The 7th period is incomplete and, like the 6th period, would have a theoretical maximum on the basis of quantum numbers of 32 elements. In this form of periodic table, 14 elements of both 6th and 7th period, lanthanoids and actinoids respectively, are placed in separate panels at the bottom. 3.4 Nomenclature of elements with atomic numbers greater than 100. The naming of the new elements had been traditionally the privilege of the discoverer or discoverers, and suggested name was ratified by IUPAC. In recent years, this has led to some controversy. The new elements with very high atomic numbers are so unstable that only minute quantities, sometimes only a few atoms of them, are obtained. Their synthesis and characterization therefore require highly sophisticated, costly equipments and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting reliable data on the new element, at times get tempted to claim for its discovery. For example, both American and Soviet Union scientists claimed the credit for discovering the element 104. The Americans called it rutherfordium, while the Soviets called it Kurchatovium. To avoid such problems, the IUPAC had made recommendation that until new elements discovery is proved, this name is officially recognized. A systematic nomenclature be derived directly from the atomic number of the element using the numerical roots for 0 and the numbers 1 to 9. This is shown in table 8.4. The roots are put together in the order of digits which make up the atomic number, and EM is added at the end. The IUPAC names for element with Z above 0 are shown in table 3.5. Thus, the new element first gets a temporary name with symbol consisting of the 3 letters. The later permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country or state of the country in which the element was discovered or pay tribute to a notable scientist. As of now, elements with atomic number up to 118 have been discovered. Official names of all elements have been announced by IUPAC. Problem 3.1. What would be the IUPAC name and symbol for the element with atomic number 120? Solution. The root for 1, 2 and 0 are un, bi and nil. Respectively, the symbol and name respectively are UBN and unbinilium. 3.5 Electronic configurations of the elements and the periodic table. In the preceding unit, we have learned that an electron in an atom is characterized by a set of 4 quantum numbers, and a principal quantum number defines the mean energy level known as shell. We also have studied about the filling of the electrons into different subshells, also referred to as orbitals, in an atom. The distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. In this section, we will observe the direct connection between the electronic configuration of the elements and the long form of the periodic table. A. Electronic configuration and period. The period indicates the value of n for the outermost or valence shell. In other words, the successive period in the periodic table is associated with the filling of next higher principal energy level. It can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period, where n is equal to 1, starts with the filling of lowest level 1s and therefore 2 elements, hydrogen 1s1 and helium 1s2, when the first shell is completed. The second period, for n is equal to 2, starts with lithium and the third electron enters the 2s orbital. The next element, beryllium, has 4 electrons and has the electronic configuration as 1s2, 2s2. Starting from the next element, boron, the 2p orbitals are filled with electrons when the lth shell is completed at neon. Thus, there are 8 elements in the second period. The third period, where n is equal to 3, begins at sodium and added electrons enters 3s orbital. Successive filling 3s and 3p orbitals give rise to the third period of 8 elements from sodium to argon. The fourth period for n is equal to 4 starts at potassium and added electrons fill up the 4s orbital. Now you may note that before the 4p is filled, filling of 3d orbitals becomes energetically favorable and we come across the so-called 3d transition series of the elements. This starts from scandium, which has electronic configuration 3d1 4s2, and the 3d orbitals are filled at zinc with electronic configuration 3d10 4s2. The fourth period ends at krypton with the filling up of 4p orbitals. Altogether, we have 18 elements in this fourth period. The fifth period, n is equal to 5, beginning from rubidium, is similar to the fourth period and contains 4d transition series starting by deuterium. This period ends at xenon with filling up of 5p orbitals. The sixth period, which is n is equal to 6, contains 32 elements and successive electrons enter 6s, 4p, 5d and 6p orbitals. In order, filling up of the 4f orbitals begins with cerium and ends at lutetium to give the 4f inner transition series, which is called an lanthanoid series. The seventh period for n is equal to 7 is similar to the sixth period, and the successive filling up of the 7s, 5f, 6d and 7p orbitals and includes one of the most man-made radioactive elements. This period will end at the element with atomic number 118, which would belong to the noble gas family. Filling up of the 5f orbitals after actinium gives the 5f inner transition series known as actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Problem 3.2. How would you justify the presence of 18 elements in the fifth period of the periodic table? Solution. When n is equal to 5, L is equal to 0, 1, 2, 3. The order in which the energy of the available orbitals 4d, 5s and 5p increases is 5s is less than 4d is less than 5p. The total number of orbitals available are 9. The maximum number of electrons that can be accommodated is 18, and therefore 18 elements are there in the fifth period. B. Group-wise electronic configuration. Elements have same vertical column or group and have similar valential electronic configurations, the same number of electrons in the outer orbital and similar properties. For example, group 1 elements, that is alkali metals, have ns1 valential electronic configuration as shown below. Thus it can be seen that the properties of the element have periodic dependence upon its atomic number and not on relative atomic mass. 3.6 Electronic configuration and types of elements, SPTF blocks. The Aufbau principle and the electronic configuration of atoms provide a theoretical foundation of the periodic classification. The elements in the vertical column of the periodic table constitute a group or family and exhibit similar chemical behavior. This similarities arises because of these elements have same number and same distribution of electrons in the outermost orbitals. We can classify the elements into 4 blocks, that is S block, P block, D block and F block, depending upon the type of atomic orbitals that are filled with electrons. This is illustrated in figure 3.3. We notice 2 exceptions to this categorization. Strictly, helium belongs to the S block but its positioning in the P block along with other 18 elements is justified because it has a completely filled valence shell and as a result exhibits properties characteristic of other noble gases. The other exception is hydrogen. It has only one s electron and hence can be placed in group 1. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to group 17, that is the halogen family elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure 3.2 and figure 3.3. We will briefly discuss the salient features of 4 types of elements marked in the periodic table. More about these elements will be discussed later. During the description of the features, certain terminology has been used, which has been classified in section 3.7. 3.6.1 The S block elements. The elements of group 1, that is alkali metals, and group 2, that is alkaline earth metals, have ns1 and NS2 outermost electronic configuration belonging to the S block elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electron readily to form 1+ ion in case of alkali metals or 2+ ion in the case of alkaline earth metals. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found in pure nature. The compounds of S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. 3.6.2 The P block elements. The P block elements comprise those belonging to group 13 to 18, and these together with the S block are called the representative elements or main group elements. The outermost electronic configuration varies from NS2-NP1 to NS2-NP6 in each period. At the end of each period is a noble gas element with closed valence shell NS2-NP6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by addition or removal of electrons. The noble gas thus exhibit very low chemical reactivity. Preceding the noble gas family are the two important groups of nonmetals. They are halogens, that is group 17, and the chalcogens, that is group 16. These two groups of elements have highly negative electron gain enthalpy and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The non-metallic character increases as we move from left to right across a period, and metallic character increases as we dog down the group. 3.6.3 The D block elements or the transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by filling of inner d orbitals by electrons and therefore referred to as d block elements. These elements have the general outer electronic configuration as n-1 d1 to 10 ns0 to 2. They are all metals. They mostly form colored iron, exhibit variable valence oxidation state, paramagnetism, and oftenly used as catalyst. However, zinc, cadmium and mercury, which have electronic configuration as n-1 d10 ns2, do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metals of S block and less active elements of group 13 and 14, and thus take their familiar name as transition elements. 3.6.4 The F block elements or the inner transition elements. The two rows of elements at the bottom of the periodic table, called the lanthanoids, that is from cerium to lutetium, and actinoids from thorium to lawrencium, are characterized by the outer electronic configuration as n-2 f1 to 14, n-d1 d0 to 1, and ns2. The outermost electron added to each element is filled in the f orbital. These two series of the elements are called inner transition elements or the F block elements. They are all metals. Within each series, the properties of elements are quite similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids due to large number of oxidation states possible for each actinoid element. Actinoid elements are radioactive. Many of the actinoid elements have been made only in nanogram quantities or even less than nuclear reactions, and their chemistry is not fully studied. These elements after uranium are known as trans-uranium elements. I'm skipping problem 3.3 for you to solve it later, or you may pause the video and solve it right now. 3.6.5 Metals, nonmetals and metalloids. In addition to displaying the classification of elements into S, P, D and F blocks, shows another broad classification of elements based on their properties. The elements can be divided into metals and nonmetals. Metals comprise more than 78% of all elements and appear on the left side of the periodic table. Metals are usually solid at room temperature. Mercury is an exception. Gallium and cesium also have very low melting points. Metals usually have high melting point and boiling point. They are good conductors of heat and electricity. They are malleable, that is, can be flattened into thin sheets by hammering, and ductile, that is, can be drawn into wires. In contrast, nonmetals are located at the top right-hand side of the periodic table. In fact, in a horizontal row, the properties of elements change from metallic on the left to non-metallic on the right. Nonmetals are usually solid or gases at room temperature with low melting and boiling points. Boron and carbon are exceptions. They are poor conductors of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group, and the non-metallic character increases as one goes from left to right across the periodic table. The change from metallic to non-metallic character is not abrupt, as shown by thick zigzag lines in figure 3.3. The elements, for example, silicon, germanium, arsenic, antimony, and tellurium, bordering this line and running diagonally across the periodic table, show properties that are characteristic of both metals and non-metals. These elements are called semimetals or metalloids. Problem 3.4. Considering the atomic number and position in the periodic table, arrange the following elements in increasing order of metallic character: silicon, beryllium, magnesium, sodium, and phosphorus. The metallic character increases down the group and decreases along a period as we move from left to right. Hence, the order of increasing metallic character is: phosphorus is less than silicon, is less than beryllium, is less than magnesium, is less than sodium. 3.7. Periodic tense and periodic properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in group 17 non-metals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of non-metals, say halogen, reactivity decreases down the group. But why do properties of elements follow these trends? And how can we explain periodicity? To answer these questions, we must look into the theories of atomic structure and properties of atom. In this section, we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. 3.7.1 Trends in physical properties. There are numerous physical properties of elements such as melting and boiling points, heat of fusion and vaporization, energy of atomization, etc., which show periodic variations. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity. Number A. Atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than measuring the radius of a ball. Do you know why? Firstly, because the size of an atom is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. In practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value the covalent radius of the element can be calculated. For example, the bond distance in chlorine molecule is 198 picometer, and half the distance, that is 99 picometer, is taken as the atomic radius of chlorine. For metals, we define the term metallic radius, which is taken as half of the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometer. Here, the metallic radius of copper is assigned the value of 128 picometer. For simplicity, in this book, we use the term atomic radius to refer both covalent and metallic radius, depending on whether the element is non-metal or metal. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic radii of a few elements are listed in table 3.6. Two trends are obvious. We can explain these trends in the term of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in figure 3.4a. For the elements of the second period, it is because within the period of the outer electrons are in the same valence shell and the effective nuclear charge increases as atomic number increases, resulting in increased attraction of electrons to the nucleus. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number as illustrated in figure 3.4b. For alkali metals and halogens, as we descend the group, the principal quantum number n increases and the valence electrons are farther from the nucleus. This happens because the inner energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in atomic radii. Note that the atomic radii of noble gases are not considered here. Being monoatomic, their values are very large. In fact, the radii of noble gases could be compared not with the covalent radii but with the van der Waals radii of other elements. B. Ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of electron leads to an ion. The ionic radii can be estimated by measuring the distance between the cations and anions in ionic crystals. In general, the ionic radii of elements exhibit the same trend as that of atomic radii. The cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. For example, ionic radii of fluoride ion F- is 136 picometer, whereas the atomic radius of fluorine is only 64 picometer. On the other hand, the atomic radius of sodium is 186 picometer compared to the ionic radii of 95 picometer for Na+. When we find some atoms and ions which contain same number of electrons, we call them isoelectronic species. For example, O2-, F-, Na+, and Mg2+ have same number of electrons, that is 10. The radii would be different because of the different nuclear charges. The cation with greater positive charge will have the smaller radius because of the greater attraction of electrons to the nucleus. An ion with greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. Problem 3.5. Which of the following species will have the largest and smallest size? Mg, Mg2+, Al, Al3+. Solution. Atomic radii decrease across a period. Cations are smaller than the parent atom. Among the isoelectronic species, the one with larger positive nuclear charge will have a smaller radius. Hence, the largest species is Mg and the smallest is Al3+. C. Ionization enthalpy. The quantitative measure of tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom in its ground state. In other words, the first ionization enthalpy of an element X is the enthalpy change for the reaction depicted in the equation X changes to X plus electron. The ionization enthalpy is expressed in the units of kilojoule per mole. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in the equation 3.2. The energy is always required to remove electrons from an atom and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from positively charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be lighter than the second and so on. The term ionization enthalpy is not qualified, it is taken as the first ionization enthalpy. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted in figure 3.5. The periodicity of the graph is quite striking. You will find maxima at the noble gases which have closed electron shells and very stable electronic configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpy can be correlated with their high reactivity. In addition, you will notice two trends in the first ionization enthalpy. Generally increases as we grow across the period and decreases as we descend in a group. These trends are illustrated in figure 3.6a and b, respectively for the elements of the second period and first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors. Number 1, the attraction of electrons towards the nucleus, and number 2, the repulsion of electrons from each other. The effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of the shielding or screening of the valence electrons from the nucleus by intervening core electrons. For example, the 2s electron in lithium is shielded by the nucleus by the inner core of 1s electrons. As a result, the valence shell electron experiences a net positive charge which is less than the actual charge of plus 3. In general, shielding is effective when the orbitals in the inner shells are completely filled. The situation occurs in the case of alkali metals which have single outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine, across a period successive electrons are added to orbitals in the same principal level, and the shielding of the nuclear charge by inner core electrons does not increase very much to compensate for the increased attraction of the electron to the nucleus. Thus, across a period increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly and the ionization enthalpy increases across a period. As we go down a group, the outermost electron being increasingly farther from the nucleus, there is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge and the removal of the outermost electron requires less energy down a group. From figure 3.6a, you will also notice that the first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has greater nuclear charge. When we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed from the ionization is an s electron, whereas the electron removed during ionization of boron is a p electron. The penetration of the s electron and the nucleus is more than that of 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove 2p electron from the boron compound to the removal of 2s electron from the beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the first ionization enthalpy of oxygen compared to nitrogen. This arises because in nitrogen atom the 3p electrons inside different atomic orbitals as per the Hund rule, whereas in oxygen atom 2 of the 4 2p electrons must occupy the same 2p, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the 4th 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. Problem 3.6. The first ionization enthalpy values of third period elements sodium, magnesium and silicon are respectively 496, 737 and 786 kJ per mole. Predict whether the first ionization enthalpy value for aluminium will be close to 575 or 760 kJ per mole. Justify your answer. Solution: it will be more close to 575 kJ per mole. The value for aluminium should be lower than that of magnesium because of effective shielding of 3p electrons from the nucleus by 3s electrons. Number D. Electron gain enthalpy. When an electron is added to a neutral gaseous atom to convert it into a negative ion, the enthalpy change accompanying the process is defined as electron gain enthalpy. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion as represented by the equation 3.3. Depending on the element, the process of adding an electron to an atom can either be endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements, the halogens, have very high negative electron gain enthalpies because they can establish noble gas electronic configuration by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that the electron gain enthalpies have high negative values towards the upper right of the periodic table preceding the noble gases. Variation in electron gain enthalpies of the element is less systematic than for the ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group, because the size of an atom increases and the added electron would be farther from the nucleus. This is generally the case. However, electron gain enthalpy of oxygen or fluorine is less negative than that of the succeeding element. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller n equals to 2 quantum number and suffers significant repulsion from the other electrons present at this level. For n equals to 3 quantum level, like sulfur or chlorine, the added electron occupies a larger region of the space and the electron-electron repulsion is much less. Problem 3.7. Which of the following will have the most negative electron gain enthalpy and which the least negative? Phosphorus, sulfur, chlorine, fluorine. Explain your answer. Solution. Electron gain enthalpy generally becomes more negative across a period as we move from left to right. Within a group, electron gain enthalpy becomes less negative down the group. However, adding an electron to the 2p orbital leads to greater repulsion than adding an electron to the larger 3p orbital. Hence, the element with most negative electron gain enthalpy is chlorine and the one with least negative electron gain enthalpy is phosphorus. Number E. Electronegativity. The qualitative measure of the availability of an atom in a chemical compound to attract shared pair of electrons towards itself is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, number of numerical scales of electronegativity of elements, for example, Pauling scale, Millikan-Zafir scale, Alfred-Rorschach scale, have been developed. The one which is most widely used is the Pauling scale. By Linus Pauling, an American scientist in 1922 assigned arbitrary value to 4 to fluorine and the element considered to have greatest ability to attract the electrons. Approximate values for the electronegativity of new elements have been given in table 3.8a. The electronegativity of any element is not constant. It varies depending upon the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together, a relationship that we will explore later. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decreases down the group, say from fluorine to astatine, in the periodic table. How can these trends be explained? Can the electronegativity be related to atomic radii, which tend to decrease across a period each from left to right but increase down the each group? The attraction between the outer or valence electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases. On the same account, electronegativity values decrease with the increase in atomic radii down the group. The trend is similar to that of ionization enthalpy. Knowing the relationship between electronegativity and atomic radius, can you now visualize the relationship between electronegativity and non-metallic properties? Non-metallic elements have strong tendency to gain electrons. Therefore, electronegativity is directly related to that non-metallic properties of elements. It can be further extended to say that the electronegativity is inversely related to the metallic properties of elements. Similarly, the decrease in the electronegativity down the group is accompanied by a decrease in non-metallic properties or increase in metallic properties of elements. All these periodic trends are summarized in figure 3.7. 3.7.2 Periodic trends in chemical properties. Most of the trends in chemical properties of elements such as diagonal relationship, inert pair effect, effects of lanthanide contraction, etc. will be dealt with along the discussion of each group later in the units. In this section, we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period elements from lithium to fluorine. A. Periodicity of valence or oxidation states. The valence is the most characteristic property of elements and can be understood in terms of their electronic configurations. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and or equal to the 8 minus number of outermost electrons as shown below. Nowadays, the term oxidation state is frequently used for valence. Consider the two oxygen-containing compounds OF2 and Na2O. The order of electronegativity of the three elements involved in these compounds is fluorine is greater than oxygen is greater than sodium. Each of the atoms of fluorine with outer electronic configuration as 2s2 2p5 shares one electron with oxygen in the OF2 molecule. Being highest electronegative element, fluorine is given oxidation state as -1. Since there are two fluorine atoms in this molecule, oxygen with outer electronic configuration 2s2 2p4 shares two electrons with fluorine atoms and thereby exhibits +2 oxidation state. In Na2O, oxygen being more electronegative accepts two electrons from each of the two sodium atoms and thus oxidation state -2. On the other hand, sodium with electronic configuration 3s1 loses one electron to oxygen and is given oxidation state +1. Thus, the oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from the other atoms of the molecule. Problem 3.8. Using the periodic table, predict the formulas of compound which might be formed by using the following pairs of elements: A. Silicon and bromine, B. Aluminium and sulfur. Solution: A. Silicon is a group 14 element with a valence 4. Bromine belongs to the halogen family with valence of 1. Thus, the formula for the compound formed would be SiBr4. Number B. Aluminium belongs to group 13 with valence of 3 and sulfur belongs to group 16 with valence of 2. Hence, the compound should have the formula of Al2S3. Some periodic trends observed in the valence of elements, hydrides and oxides are shown in figure 3.9. Other such periodic trends which occurs in the chemical behavior of the elements are discussed elsewhere in this book. There are many elements which exhibit variable valence. This is particularly the characteristic of transition elements and actinoids, which we shall study later. Number B. Anomalous properties of second period elements. The first element of each of the following groups 1 and 2 and groups 13 to 17 differs in many respects from each others of the respective group. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, forms compound with pronounced covalent character, and other members of the group predominantly from ionic compounds. In fact, the behavior of lithium and beryllium is more similar to the second element of the following group, that is magnesium and aluminium respectively. The sort of similarity is commonly referred to as diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior of the first member of the group of elements in the S and P blocks compared to that of the subsequent members in the same group? The anomalous behavior is attributed to the small size, large charges to radius ratio, and high electronegativity of the elements. In addition, the first member of the group has only 4 valence orbitals, that is 2s and 2p, available for bonding, whereas the second member of the groups have 9 valence orbitals, that is 3s, 3p and 3d. As a consequence of this, the maximum covalency of the first member of each group is 4. For example, boron can only form Bf4-, whereas other elements of the group can expand their valence shell up to accommodation of more than 4 pair of electrons, for example, aluminium with Alf63-. Furthermore, the first member of the p block element displays greater ability to form p-pi multiple bonds to itself and to other second period elements compared to the subsequent group members of the same group. Problem 3.9. What are the oxidation state and covalency of aluminium in AlCl2O5 2+? Solution. No, the oxidation state of Al is +3 and the covalency is 6. 3.7.3. Periodic trends and chemical reactivity. We have observed the periodic trends in certain fundamental properties such as atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and valence. We know by now that the periodicity is related to the electronic configuration. That is, all elements with chemical and physical properties are a manifestation of the electronic configuration of the elements. We shall now try to explore relationship between these fundamental properties of the elements with their chemical reactivity. The atomic and ionic radii, as we know, generally decrease in a period from left to right, and as a consequence, the ionization enthalpy generally increase with some exceptions as outlined, and ionization gain and electron gain enthalpies become more negative across a period. In other words, ionization enthalpy of the extreme left element in a periodic table is least and the electron gain enthalpy of the element on the extreme right is highest negative. Note that noble gases having completely filled shells have rather positive electron gain enthalpy values. This results into high chemical reactivity at the two extremes and lowest in the center. Thus, the maximum chemical reactivity at the extreme left is exhibited by loss of an electron leading to the formation of a cation, and at the extreme right is shown by a gain of an electron forming an anion. This property can be related with the reducing and oxidizing behavior of the elements, which you will learn later. However, they can be directly related to the metallic and non-metallic character of the elements. Thus, the metallic character of an element which is highest at the extremely left decreases and the non-metallic character increases while moving from left to right across a period. The chemical reactivity of an element can be best shown by its reactions with oxygen and halogens. Here we shall consider the reaction of elements with oxygen only. Elements on the two extremes of the period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is most basic, whereas that formed by the element on extreme right is most acidic. Oxides of elements in the center are amphoteric or neutral. Amphoteric oxides behave as acid with bases and basic with acids, whereas neutral oxides have no acidic or basic properties. I'm skipping problem 3.10 for you to solve it later, or you may pause the video and solve it right now. Among transition metals, the 3D series, the change in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller than inner transition metals. The ionization enthalpies are intermediate between those of S and P blocks. As a consequence, there are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in gradual decrease in ionization enthalpy and a regular decrease with exception in some third period elements as shown in the section 3.7.1. In electron gain enthalpies in the case of pain group elements, thus the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property, which you will learn later. In the case of transition elements, however, a reverse trend is observed. It can be explained in terms of atomic size and ionization enthalpy. Summary. In this unit, you have studied the development of the periodic law and the periodic table. Mendeleev's periodic table has been based on atomic masses. Modern periodic table arranges the elements in the order of their atomic numbers in the given horizontal rows and 18 vertical columns as groups or families. Atomic number in a period are consecutive, whereas in a group they increase in a pattern. Elements of the same group have similar valence shell electronic configuration and therefore exhibit similar chemical properties. However, elements of the same period have incrementally increasing number of electrons from left to right and therefore have different valencies. 4 types of elements can be recognized in the periodic table on the basis of their electronic configurations. These are S block, P block, D block, and F block elements. Hydrogen with 1 electron in the Valence orbital occupies the unique position in the periodic table. Metals comprise more than 78% of the known masses. Non-metals, which are located at the top of the periodic table, are less than in 20 in number. Elements which lie at the borderline between the metals and non-metals are called metalloids or semi-metals. Metallic character increases with increasing atomic number in the group, whereas decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electronegativity, and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increases across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies in general become more negative across a period and less negative down the group. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbital or 8 minus the number. Chemical reactivity is highest at the two extremes of the periodic table and is lowest at the center. The reactivity on the left extreme of the period is because of the ease of electron loss, or highly reactive elements do not occur in nature in free state. They usually occur in combined form. Oxides formed of elements on the left are basic and that of the elements on the right are acidic in nature. Oxides of element at the center are amphoteric or neutral. So that's the end of the chapter. I hope you enjoyed listening to the audiobook. We'll see you in the next one. Till then, subscribe to the channel and stay tuned. Thank you.